so it's recording anyways. So hello, welcome to new day, new problem. Today we're going to do this problem called 199 binary tree search, binary right side view, whatever. So yeah, we're going to do that right about now. So right side view.py. Okay, cool. Yeah, we're just gonna solve this. Save. Alright, anyway, yeah, we're gonna solve this. So given the root of a binary tree, imagine yourself standing on the right side of it. Return the values of the nodes you can see, ordered from top to bottom. Okay, so that's an interesting problem. So our input is just roots of bt, then our output. I don't know what our output is. What is our output? Output, what is it, a list? List of nodes, so list of nodes. That's cool. List of nodes by their values. List of node dot val. Okay, cool. And then to note, we need to solve this. Only return a list of node dot val where you can see right side. Now this doesn't mean return right, but just means return what you can see from right. Yeah, meaning I guess like, let's just say Jamboard. Yeah, let's just say we have a tree kind of like this, 1 2 1 2 5 1 3 4. So 1 2 3 4 and 5, right? So with this we can only see 1 3 and 4 from the right side. So we just return 1 3 4. But if this 4 wasn't here, then we would return 1 3 5 because we can see it from the right? Because there's nothing blocking here. So if there's nothing blocking, so if nothing blocking right side vision, add to list. Yeah, so just like that. So that makes sense. We're going through the example as well as a note. So this is okay. Let me think. And I guess if we have something more complex, it's like 1 2 3, then like 4. Oops, then like 4 5 6 7, like 8, right? Just putting it that way, right? So what can we see on the right side if we're like right here as a person, right? What can we see? Well, we can see this one. This one is, we can see it already. We can see this 2. We can see this 3, but we can't see this 5 or this 4. But we can see this 6, 7, and 8. So despite them going left, we can still see them, right? So yeah, we just need to figure that way out. But one thing that I want to realize is that I guess we can say in the match, always try right first. Always try right first. And yeah, so always try right first, because more likely to be seen, I guess. So yeah, so that's one thing. So yeah, for the example, we'll just return 1 1 2 3 6 7 8, right? So yeah, yeah, so we went through some examples, we kind of took some notes. So that's some questions. So I guess the question is, what's the min size of binary tree? And let's go check. So min size is 0. 0, cool. So we know the input output, we took some notes. of what it means to see from the right side. We have some questions, and now I went through an example, I guess, as we were kind of going through it as taking notes. So yeah, that makes sense. So yeah, let's just go ahead and kind of make a plan, I guess, or continue matching as we plan. So first things first, I know for sure when we did that first search. So that first search, but I'm not sure what to take in. Well, we'll definitely take in a node. Let me think. Maybe a level. Take in level as well. I'd say level because one level can only see one node, right? Because it makes sense, right? So in a binary tree, we only have 2 paths. But if this was like just like a tree, like 3, if this was a tree, and we're only on the right side, we can only see this 2 anyways. So that makes sense, right? So yeah, that makes sense. Level because one level can only see 1 node. That makes sense. And then we're going to have resulting list. This will help us determine what level we have currently. So for example, right, let me just remove this 3. I think this is a better one. So for example, let me think of how to word this. So let me just start out our initial example, like how I want it to be said. So let's say we already have 1 and 3, and we're doing recursion, right? So we're on the right side still. On the right side, because left side, we already said that we already have something here at level 1, or level 2, I guess. So we're not going to do anything with this 2. We're not going to add it or anything. But here we're at this 3. This 3 is like, okay, I need to check my right and left. Hold up, I need to. All right. Anyways, so I was busy. Anyways, I think where was I? Yeah, I was at the part where we're at this 3. You have to go left or right, right? But initially, we want to go right first because we just want to check that first. So basically, when this 3 is done, it gets inputted in here. We're like, okay, so let's go to the right. There's nothing at the right, right? So what do we do? Well, nothing gets inputted here, so we check its left. And I'm like, okay, there's nothing here, so what do we do now? Then I'm guessing that from the top, the right is done, so we have to go through the left now. So 2 does exist on the left, but there already is something in its level position in the resulting list, so we don't put it in there, but we still just keep on going. So I'm guessing that this 2, it could either point left or right, doesn't really matter. It points right first, then there's nothing there, so we don't do anything there. But then we have to go through the left. I'm like, okay, so there is something here. So what we're going to do is we're going to check if there is space for it, I guess. Yeah, if there is space for it. There's nothing in this position. So what we can do is we can put it there, right? So 5. And so on. And then we check its left and right. We check its right and left, and nothing there, so we just stop. And then we return this list. So yeah, that's what's going to happen. So let me just plan it out. Kind of go through it with some pseudocode with what I just talked about. So first off, we're gonna have a resulting list. So initialize result list to hold what we can see from right side of BT. So this is a comment. So damn, song's good. So res equal to empty list. And then we're going to have a function to solve this. So that first search, we're going to take in a node that we're given and the level we're given. And the first thing I want to do is say if null node stop, and then if we don't stop, then if it's not a null node, first we want to do is to access a cur node to check if in res or not. Then check if can put or not. So put no right side yet, or can see from right side or not, which is already something already there. Current node blocked. Yeah, I guess. So to access current node, to check if in res or not, to check if we can put it there, if it's visible from the right side. Oh no, I guess I'm gonna say, just reword it. So access cur node.eval. See if can see from right side. True is equal to put in res. Right side from level. True is put in res. False is equal to do nothing. So let's see that. So I'm gonna say like. So first off, we need to check if it's there in the level. But to do that, we need to check the length, right? So initially, when we start off with an empty list, because that's what we're gonna do. We're gonna say, so if length of res less than our level, right? So if the length of the res is less than our level, because this is technically level 1, and that means that there's nothing there, so we can put something there. So we're going to put we're going to append, so res.append cur.val, right? Else nothing, right? That's basically it. Then we have to call right and left, so dfs cur.right with the level incremented by 1, and then cur left incremented by 1. So this is how the algorithm is going to be like. Let's just do it again, but make it faster this time. So let me just remove these. I wish there's a better tool for this. I mean, I could use Photoshop, but like that's just too much, or just this stuff. Probably look something up. So here we're given this binary tree. This is our example. Then we access our first node. But like if length res less than our level, we're given level 1. So we're given level of 1. So if length less than level, which is true, 0 is less than 1, then we're going to append it to our list. So 1, right? Because that's the first thing that we see. And then we go to the right and then we do the same thing. If length less than level, if 1 less than 2, then put it in there. So then we have 3. Okay. Then we go to 3's right, nothing there. So if null's no, if null no, then stop. Then we go through its left. If null no, then stop. So then we're back to this 1. We have to go through the left. Then we arrive at this 2, and we say if length of the list is less than level. Currently the length of the list is 2, the level is 1. This is not the case, so we don't do anything. We just go to its right. Then we say when we arrive at its right, the node is null, so we just stop. Then we go to its left, and we say if length of the list is less than level, this is level 3, right? Length of the list is 2. Then we append. Okay, so we basically append it into the list, and then now we have 1, 3, 5. And now we have to check 5's right. There's nothing there. Check its left, nothing's there. So then we're done. Alright, so we're basically done here. We stop recursion entirely. Now res should be 1, 3, 5. So now all we gotta do is return res. So yeah, that's kind of the whole code, or our pseudocode. So yeah, let's just go ahead and kind of code it up. It should work according to what we just went through. So let's just go ahead and copy and paste it here as a plan in LeetCode. Cool. So first step is to initialize res. So res is equal to an empty list. Then we have to create our def first search function. So DFS will take in a node and a level. And then in our def first search function, we want to in our DFS function, we want to check. This is our base case. If our node is null, if it is, then do nothing. So if not node, then return. Just stop. And then if it doesn't go through our base case, then we can kind of see if we can see the node from the right side. If we can, then append it. If not, then do nothing. So if we can see it, so if length of our list is less than the level we're given, then append it into our resulting list. So no.val. Else, if we can't see it, then do nothing. So if can see it, then add. If can't see it, do nothing. And then once we're out of that if statement, this looks weird. Like, I feel like this is not right. It feels off. Off by 1. I feel like this is off by 1. Am I tripping? It is off by 1, but how? The heck? I don't know what's going on. It's kind of bothering me. Is it? Or I don't even know. I can't tell. Anyways, this should be fine. Either way, it's just annoying me. So yeah, so if we can see it, then add. If you can't see it, do nothing. And then we have to call its left and right. I mean right and left first. So no.right with level plus 1, and then we have to call its left to level +1. Okay, and then this is our whole function. So all we gotta do is initially call that first search on our root with level 1, and then once we call this, it should run recursion using this whole algorithm. And then our resulting list should be populated, so we're gonna return res. Yeah, so this should work. Yeah, like, why is this not right? What's wrong? Is it this? Okay, and is this one too? Okay. Okay, then submit. Yay, we did it! We did it! We did it! Yay, we did it! Alright, anyways, so enough of that cringe. So for time, to review its complexities, the time complexity is O of n because we go through every node once. For space complexity, in general, it's O of n space, I guess, because we kind of store. No, it's O of h. Yeah, it's O of h this time, because we store one node for every level. So basically, the list will have the size of the height of the binary tree we're given. Yeah, that's the first time O of H is correct. Yeah, so for time O of N, for space O of H.